Bismillahir Rahmanir Rahim. In the previous lecture, we talked about multithreading and we showed how threads can execute in parallel. Here is thread 1 serving client 1, thread 2 serving client 2, and both they access this memory within the server. And this is how we showed that client to thread 1, thread 2, they execute in parallel, and each one they take turn in the CPU using this queuing model. 3-1, like thread 1, here we have this guy, thread 1 will execute, and thread 2 would be in both in the queue. Thread 1 will come to the CPU, will execute. This is not right. Let's see, take this guy. Thread 1 will go to the CPU, will execute for a while, and after it finishes or it goes back, all right. Let me I want to grab this guy. Okay, thread 1 gets to the CPU, executes for a while, then thread 2 executes for a while, then both terminate, and we are done with the threads. This looks a very smooth operation. However, something can go wrong. Something can go wrong if both threads they enter something called a critical section at the same time. What is a critical section? A critical section would be, let me show how, would be a certain location in the memory, and the certain location in the memory can be accessed by both threads at the same time. Okay, let's say this is again, assuming this is my CPU, my processor with the memory, and let me show another place here. Okay, this is something within the memory, within my system. Let me give it black color. I will call this critical section. And by critical section, as I explained, it means it's something in your system. Let me call this for a second. It's a counter X. Okay, so this and by counter X we mean, okay, counter X means it's something like X plus plus. So I'm adding to X certain value, 1, X, let's say X was 0, 0 plus 1 is 1, plus 1 is 2, and so on. And here I have both the threads, 2 threads. Okay, this is thread 1, and I have thread 2. Okay, so what thread 1 does continuously, it makes an increment to the value X. Similarly, this guy makes an increment to the value X. This is very simple problem. Thread 1 increments X, thread 2 increments X. You can think of this as, let's say, an election process where X is the candidate, المرشح للانتخابات, وthread 1 is a voter, thread 2 is another voter. So thread 1 takes the vote, increments X. Let's say I am voting for X, so I incremented X. When thread 1 executes, let's say thread 1 when thread 1 runs, make this a bit bold and change the color. Okay, when thread 1 executes, and let me write this down here. Let's show the operation. So thread 1 executes x plus plus, which means it becomes x equals 0 plus 1, which is supposed to be 1. And then when it's done here, and so this is thread 1 and thread 2. Note that I will move this a little bit down here. When thread 2 executes, this is thread 2, it executes the same thing, x plus plus. So x now is equal to 1 plus 1 equals 2. The variable x, or the counter x, is a global variable, and this global variable is accessed by two threads, by both threads, by thread 1, thread 2, and they take turn. So now at the beginning, T1 executes x, increments it by 1, then T2 increments x by 1. Let me take this one more time. When the turn for thread 1 comes, it will execute x. Now this was 1, this should be 2. And when thread 1 finishes executing, it will give the turn for thread 2 on the CPU, and thread 2 will execute x. Now this is 2 plus 1 should be 3. If everything goes wrong, these threads will keep incrementing x every time you increment it by 1. So after certain, let's say, n steps, after 30 steps, the value of x should be 60, because I incremented by T1 30 times, by T2 30 times, so it should be 60. At this stage here, T2 should be 3. Now, if everything goes smooth, that's what we expect. Something could go wrong. What could go wrong? Let me take this slide and move it to another place. So this is my slide now. Now, let me show the following scenario. What could happen? When, let me take this out for a second. Okay, and take this one out. Okay. Now remember that x is a memory location. It's a variable, it's a memory location. X points to a certain location in memory, and it starts with a value 0. Let's say T1 executes, T1, and this is my CPU, by the way. This is, just make sure that we know this is our CPU, and this CPU is the threads, they take turn in the CPU, and when the thread finishes its time slot, let's say it's 1 millisecond or 10 milliseconds, then thread 2 will take over. Now let's say thread 1 comes to the critical section, it executes the statement x plus plus, and it exits, it comes back to the queue. And let me show, as I did before, this is my queue right here. Okay. All right, I don't need this anymore. So now when thread 1 executes, goes to the CPU, after it's done, it comes back from the CPU, it goes to the queue, Actually, let me do a different way. Okay. Okay, so the thread one, once it's done, it goes back to the queue here, and it allows T1 to T2 to execute. Now, when T2 makes the execution, x plus plus x equal 1 plus 1 equal 2, at this time, let me put this here, T2 time out. T2 time out means T2 leaves the CPU before the CPU updates the memory. So at this time, the value of x is still 1, has not been updated. Memory is not updated. Why? Because T2 leaves the CPU, comes back to the queue right here. So T2 comes here, and the value of x, let me change this now. This is x still equals 1. T2 leaves the CPU, comes back to the queue before it updates x. For some reason, it was interrupted. It did not finish its time. T2 thread 2 was a little bit late. It could not finish the complete operation. So the value of x equal to is still in the CPU. Has not, this is my memory location, has not been updated. Now T1 is going to run. Now T1 is going to run. When T1 runs, it will execute x plus plus, and it will say x equal, it was supposed to find this 1 plus 1 equal 2. That's what it was supposed to see. However, because of the synchronization problem and the synchronization time, T2 was not able to update x completely, and x would still have been at value 0 as it was here, and then it will say 0 plus 1 equal 1. Irony. 0 plus 1 equal 1. Now T1 finishes. T1 now finishes. It allows T2 to come back to the CPU to execute, and it comes from here. Okay. So now this is T2. T2 comes back to the CPU to execute, and this T2, take this from here now. That's when this is T2, will execute x plus plus. Now x is when it comes back to execute the statement, it will not do the x plus plus, it will do the store x in memory. Okay, and the value of x was 1, so it will store 1. So after executing these 4 operations, instead of having x equal 3, I will still have x equal 1. But I'm sorry, x equal 2 here, because the value was 2. So now, instead of having the value of x equal 3, I have the value of x equal 2. I have 1, 2, 3, 4 operations, 4 increments for x, instead of x equal 1, x equal 2, x equal 3, x equal 4. I mean 0, 1, 1 plus 1, 2, 2 plus 1 equal 3, and then 3 plus 1 equal 4. I have x equal 2. That is a problem. Why is the problem? Because let me show what exactly goes within x, so we can do okay, it's new slide. I will this is what happens for t1 equal x plus plus. This goes like this. Actually, it's read x from memory. Let's say x was on the point equal 0, and increment x, which means now x will be equal 0 plus 1 equals 1, and then store x into memory, which means now x equals 1 in memory. By the way, here we say increment x. Actually, this is not x. This will be read x from memory. This goes into actually load x into register r. Here I will say increment r. So r equals 0 plus 1 equal 1. It's register. And store r is more likely into memory location x. So now x equal 1. Okay, that's for T1. The same thing for T2. These are the two operations. What did I do here? Right. Okay, it will be T2. When I say equal x plus plus, read x from memory, x is 1. Load x into register r equal 1 plus 1. Store r into memory, location x, now x equals 2. That's exactly how the operation is executed. Now, when I send, when I run T1, let me take this into one more slide. Let me duplicate this slide. Okay, and let me put this in color red. So I would say here, execute T1. I execute T1. This is execute T1, which is equal x plus plus. And I will do this. These are this is step 1. Step 2, I am done. Step 3, step 4. Okay, now when I'm done with this, I will come back here and I will say execute T2 equal x plus plus. Now I will say this will go step 1. I read x from memory. Now x was 1. This is x equal 1. Let me do this in a different color just to, okay. Okay. Step 1, I read x from memory, x equal 1. I load x into register, so register now r equal 2. Now r equals 1. And I need to increment r equal 1 plus 1. So r now I increment it to 1. Now before I do that, I will do T2 times out. Okay. T2, why not? Now T2 times out. And T2 goes to the queue as I have shown here. Actually, what happened to my yeah, okay, it's right here. T2 now goes to the queue. So when I am doing here the T2 goes to the queue, which is right here, but in the memory I still have the register equals 1. I have not updated x equal 2. Now I will do execute T1. This is what will happen. I will come here. Okay. So now T2 times out, T2 goes to the queue. I will execute T1 equal x plus 1. Now this, I will repeat the same process. Read x from memory. X is still equal 0. Now x equal 1. I'm sorry. Because I already updated x equal 1 there. And I load x into register. So register r equal 1. And I will increment r to 1 plus 1. Should be equal 2. And let's say I store r into memory location x, so now x equals 2. Now at this stage, x, let's say, let me put it in black, x terminates, gets out of the CPU. Now the turn goes to T2. Now let's T2, what happens? Now I will resume, here I will say, in quotations, I will say resume the execution of T2. So T2, where I left T2 was right here, execute T2. Last time when I timed out, the value of the register was 1. So now I want to store R into memory location X. Now what's in R? What's in R was 1. This was the value of R for T2. So I will put X equal 1. Sorry, 2. Okay. So X equals 2. Now T2, this is T2. T2 completed its execution. It allowed X to be equal to, and T1 it executed the value or this part of code and X equal to. So at the end of these operations, I was supposed to have, if everything was smooth, let's say if everything went smooth, what I would have had here, okay, one more time. Why this is not happening? Let me do something else. And let me do this. Fill, no fill. So T1 would have X plus plus. So the value of X now equals 1. T2 would have X plus plus, should have been 2, and then T1 X plus plus should be 3. Instead of having X equal 3, I have X equal 2 at the end. That's my critical section problem, because X is a critical section. By critical section, I mean, let me write this down. Critical section is a memory location accessed in parallel by one or more threads. Accessed and modified, by the way. And modified. It has to be modified. If it's not modified, it doesn't matter. So it has to be a memory location like X. It's accessed in parallel by thread 1 and thread 2, or thread 1, thread 2, thread 3. It could be many more threads. They are all accessed in parallel, and all of them, they will update the value of X. However, the value, if things go all right, then they will be updating it in sequence. Otherwise, as we see, 3 operations should change X from 0 to 3. Here I have 3 operations changed X from 0 to 2. That is exactly the problem of critical section. Now, how do we solve that? In Java, there is something, let me show. In Java, there is something called synchronized. When I do the word synchronized, okay, synchronize the threads. When I do this, I use the word synchronized. In our example, the client server example, we use synchronize this, which is the current thread, and then I do for integer I equals 0 all the way to I less than the maximum client count. Okay, if thread of I not equal null and blah blah blah, then I do threads.I, a new user, etc. Enter the chat room. If for any reason this current thread, and this is thread 1 and thread 2, if thread 1 happens like, or thread 2, like in our case, happen to leave the critical section before it ends, it will block thread 1 from entering the critical section. Let me explain this in a different manner. So let me show this. Let me do the word synchronization. So in what this means for the word, let me do it in as I did before here. Control C. Okay. Here is my, here's what I have. Thread 1 got into the CPU. Now x2 times out. T2 leaves the CPU before the CPU updates the memory. The value of x is still 1. So T2 is waiting. Now here comes T1. T1 wants to come and update x. But T2 has not finished. T2 has left the value of x in the register as I showed before. So now what happens if I use the synchronization? If I use here the word synchronize, synchronized T1 and synchronized, how do you do this? Synchronized T1, and I have both are synchronized. Let me just use this syntax. This is my own syntax. Synchronized T2. Okay, so when T2 leaves the CPU and comes back here, now T1 wants to come and to update the value of x. Because T1 is synchronized with T2, this will be, I will do it this way. I will block it, and this is how I will show the block. So T1 now can no longer, and I will change this to black. Now T1 is going to be blocked. It's synchronized. It cannot come to x1. It will wait. Actually, let me do even one more trick here to show what I mean by that. I will bring this back. Okay. Actually, I'm hiding it in this manner to show that T1 could not access. It will go into the CPU. It will time out before it can reach x1. It will be blocked. So around x here, so x will be surrounded by this block. Let's put this shape here. Actually, I would put something like this. And okay, there is a barrier. So I'm putting here a barrier. And this barrier, now I will take this back and show it because I no longer need, let me bring it to the front. Oops. Bring this send backward, no, send back, bring front. Okay. So T1 now is blocked right here. It cannot go to X1. And when when T2 comes back, it will find that the value of X has not been updated. It will update it to 2. And when T1 comes back, it will find the value of, when it reads X, it will get 2 plus 1 will be 3, and everything will go smooth. So this is what we mean by the synchronization. So if I synchronize T1 and T2, every time do it one more time. So this is my critical section, and this critical section will be surrounded by block from here. So when T1 comes, or T2, this is T1, T2. So if T1 wants to access the critical section, it will be blocked by this synchronization block, and T2 will be, so when T1 comes to the critical section, let me okay, this is my critical section. Okay, so T1 access the critical section. It will be first blocked here. It will check, is T2 still in the critical section? Yes. If it's in the critical section, it has to wait on T2. When T2 wants to get in the critical section, it will wait for, it will check, has T1 finished doing its business in the critical section? If it has finished, then T2 will enter. So they will go in turn. So the critical section will be controlled by this block here, which is called synchronized. This is called synchronization. Synchronization. This synchronization wall, it will synchronization wall. This synchronization wall will synchronize the acts of T1 and T2, so no one can go in the critical section at the same time. Now, this will solve what we call, this synchronization will achieve what we call mutual, actually let me put it down. Okay, this will solve the mutual exclusion for the critical section. What do we mean by mutual exclusion? Mutual exclusion is each thread mutually excludes the other thread from entering the critical section until it's over. So that's a mutual exclusion. Exclusion means يعني بالعربي اللي هي المنع المزدوج. انه انا بمنعك، انت بتمنعني. ثريد 1 بيمنع ثريد 2، ثريد 2 بيمنع ثريد 1، اثنين بيمنعوا بعض mutual exclusion بطريقه synchronization. This is perfect. This is good. However, this creates a new problem. We solve the mutual exclusion, which means the value in the critical section, let's say the value of x, the value x, will always have the correct value, will never have the wrong value because of this. But it does create a new problem. What is the problem created the the synchronization? A new problem created by the synchronization tool. I will call it tool. What is this problem? This is called a deadlock. There is deadlock. Now, what is the deadlock? I will explain this deadlock in the next lecture. But for now, let's understand the synchronization. Please go and look at at this synchronization issue. This is synchronize threads. This is one. Look at this issue. Look at the synchronized tool. All of these, you can read them and find, actually understand what I mean by that. And now I will talk about deadlock and synchronization in the next lecture. However, I want you to understand this piece of code, this one here, what it does for you within the client server context and the chat client server chat system. Please read the code, understand it, and check with the during the session or the lab session with the TAs. You will understand this very good, and I will have an assignment on this issue for you to resolve the issue of synchronization and to understand the deadlock. So next time I will talk about deadlock and how we solve the deadlock in using Java for the client server architecture. Okay, thank you, and we'll see you next time.